So what we're talking about today are two particular nuclear reactions. So all the nuclear reactions we've done thus far in terms of balancing and talking about them have been decay reactions, okay? Reactions that just happen spontaneously because something is radioactive and it's guided by its half-life. Today we're talking about types of reactions that are related still to the nucleus, and they're known as fission and fusion, okay? So the first one we're going to focus on is the process of fission. So what fission is this is the idea of how we split an atom. Okay, so when they say that we learned how to split an atom, Albert Einstein, that group of scientists, it's not like they took a little baby knife, right, and cut open an atom.
Just like
It's not quite how it works, right? So the way that it works is like this, okay? So watch our little picture here, okay? So we start with a big atom, okay? It's really, really difficult to split things that are small, okay?
Does that mean that they release more power though if you split them?
I mean, somewhat, possibly.
So if you like split helium, would it like blow the whole one up?
They have hydrogen bombs. So.
Yes, so we'll get to hydrogen bombs and what those are, because it's different. Yeah. Okay, so the key piece you're going to see are our neutrons. Okay, neutrons are the key here in making this work. In a sense, the neutrons are like our knife. Okay, so what we do with fission is we take a neutron and we shoot it at a large unstable atom. So it's already unstable, and then we add another one to the mix. This flying neutron causes the atom to literally split itself apart because it's just so unstable. And we end up with two smaller atoms, a whole lot of energy, and then also in the process, more neutrons come shooting out because it's trying to stabilize itself again. Yeah?
So when they split into two, those aren't yet stable yet?
Yes, so when we talk about the radioactive waste that's produced, part of it are these atoms, is that they're still kind of radioactive. And then that's what we have to figure out what to do with them. Our presenter, our Navy presenter, when he came, talked about this relationship, how 1 gram of fission fuel is equivalent to 3 tons of coal. So the amount of energy that comes out of this atom splitting is crazy. But you gotta recognize, when an atomic bomb goes off, it's not just one single little atom, right? What happens, did you have a question, Kate?
Yeah, I was just wondering, like, how come so much energy is released?
Okay, from it, it's because if you remember from our video, right, a nucleus has a type of nuclear force that holds it together, that strong force, right? In our video, I talked about like the rubber bands kind of idea. And so when the atom splits, all that energy comes out. And if you remember, this is the idea of why the Einstein's equation of E equals mc squared. This is the amount of energy that comes out. But what happens is, you're totally right, like one single little atom, right, it does produce a lot of energy, but it's not just one. What makes it so big is this chain reaction idea that they then start splitting other atoms. Yeah, Nathan.
And also, part of this energy, doesn't it come from the Earth? At the beginning of the unit, we talked about how the atom has less mass than some of its parts.
Yes.
Isn't the energy that's been formed released at that point as well?
Exactly. So it's that idea of mass defect that we first talked about, right? So what we get in an atomic bomb or in a nuclear reactor, okay, is we start by shooting one neutron at the atom. Okay, that atom splits into two, but then as a result, it creates more neutrons, which then can go and cut more atoms, which then split, which release more neutrons, and that's where you get so much energy, is because you have this giant chain reaction. Yeah, Gavin.
So how come with an atomic bomb it didn't just keep going?
Ooh,
what's
great
opposite?
question. Let me show you a video right now, and then we'll talk about your question. Is they have 900 mouse traps, each with a ping pong ball on it. You'd love to be the guy to have to do that job, right? Mess up one. Okay? So the analogy here is this, okay? Each mouse trap is like an atom. okay, because there's a lot of energy stored inside, and our little ping pong balls are like the neutrons, okay?
Beautiful.
There it is. The amazing prop department here.
Yeah, boy, they must hate you right now.
All right, what we're going to do is we're going to trip this by just throwing some ping pong balls in. We'll
Okay.
see how many it takes to actually start it, and then we'll see if it can release energy.
Should we throw them all at once or throw them individually?
Let's start with one and go from there.
Okay, all right.
So it's also actually a model for Newton's third law. It's a model for how fission works. It's a really big.
Okay, nothing happened.
You got your lob.
Oh, you got a lot. Okay, all right.
Go ahead.
Let me lob. Oh. Thank you, Science Bob. We'll be right back.
I think we should do one more time. So, in an idea, that's like our chain reaction inside a nuclear reactor or an atomic bomb, right? So, to answer Gavin's question, okay, what would happen in this exact thing if they would have spread the mousetraps out and they wouldn't have been all close to each other?
It would have fit maybe one or two. But not
Yeah,
all.
like the chance of it setting off another one, right, greatly decreases the more they're spread out. So that's why an atomic bomb eventually stops, is because what we run out of is what is known as the critical mass. So in order to get this to happen, you have to have a certain amount of mass that's concentrated enough, otherwise it just stops. So all the atoms outside of the atomic bomb are not concentrated enough to get them to split. Right, so that's fission. The way we identify fission is you have one big thing to start with, and it's breaking apart into two smaller. Okay? The opposite now is the process of fusion. Okay, an easy way to help you keep them straight is think of fusion as you're fusing. Okay? So fusion is joining two smaller nuclei into one larger one. Okay? So instead of taking one and splitting it, we're actually now taking two and hooking them together. Okay? An interesting thing with this is, so you're going to see that you're starting with two different atoms to begin with, two different nuclei. Okay? Those two nuclei collide with enough energy, and we'll talk about how much is necessary. Okay? It's not like two scientists can just take atoms and be like, okay, ready? And throw them together and fusion happens. Yeah, Russell.
Doesn't this release like a ton more energy than fusion?
Yes. So this,
So stars
and we'll
do
look
this
at that, is the hydrogen bomb, and it's also what happens in the stars. Yep. And the amount of energy by fusing them together is crazy how much more it is. All right, so in order for this to happen, like we said, it's not as easy as it sounds, right? It's not just throwing two things together and they stick. Because they're not just sticking, they're making something new, okay? So often my analogy, I think of the difference between a nuclear reaction and a chemical reaction, okay? Is we'll go back, think of Legos, okay? Chemical reactions are taking a red and a blue Lego and stacking them together. And we have a molecule. A chemical reaction, fusion, would be taking a red and a blue Lego, they slam together and they turn into one orange Lego. Okay? Like, it's something totally new. They're not just like hooked together, right? It's actually something brand new. Okay? So in order for this to happen, we have to be at what is known as thermonuclear, okay, which is the temperature of 40 million Kelvin. Otherwise, you cannot sustain hydrogen fusion. In terms of something you'd understand, it's 72 million degrees Fahrenheit. So yeah, this isn't something that is just 72 million, yeah. Second, but anyone remember, so with fission, what was the relationship? It was for every 1 gram we got
3.
3. Now it's for every 1 gram of fusion fuel is corresponded to 20 tons of total coal.
So is it kind of like you have to heat it up to this point and then it goes?
And then even more is released, yeah. Yeah. So with this idea of fusion, if you don't have enough energy, it's just going to bond chemically. Without enough energy, you can't fuse the nuclei into one. And like Gavin brought up for us, to give you an idea of how much energy this is, fusion is the process that happens in the stars. The light and heat we get from our sun is because of fusion, because fusion is constantly happening. Is when inside the sun and the stars, hydrogen is constantly fusing into helium. And then what happens is eventually those fuse, bigger stars create bigger nuclei, and so the only atom that we can't credit to the stars is hydrogen, because hydrogen can't be fused because it only has 1 proton. Another little video about stars, and we'll see that, yeah, once it gets to a point, iron is actually the dying point of a typical star. That after iron, they're too heavy in that they can't fuse anymore. So how we get the rest of the elements on the periodic table is the supernova. Yeah, so we'll watch that now.
What if we set up a supernova? How many tons of coal would that?
So there is a way for stars to die out.
Yes.
So on Earth, can we not fuse iron together like in typical?
Not sustainable.
All the atoms in the universe heavier than hydrogen and helium, forged by stars.
Stars are really interesting. They don't just sit there. They don't that because they last so much longer than we do. We think they're permanent.
Stars are the ultimate alchemists. They turn light elements into heavier ones. They get the energy that they need to glow that way. A star begins its life made out of hydrogen and helium mostly. About 70% hydrogen, 28% helium in the case of the sun.
In a star's core, the temperature and pressure are so high that hydrogen atoms fuse together to make helium. Hydrogen fusion releases prodigious amounts of energy, the heat and light of a star.
That's the story for 90% of the life of a star, fusing hydrogen to make helium.
Eventually, though, the star runs out of hydrogen and begins to fuse its stocks of helium, making yet heavier elements.
And so the way it works, and it always works this way, is that it contracts and it gets hotter. And if it can find something new to burn, whether it's the kitchen sink or coal or whatever, it'll burn it.
Helium is taken 3 at a time to make carbon.
You can add 1 more helium to that carbon and make element number 8, oxygen.
That's a tremendous step forward. We get carbon and nitrogen and oxygen made in stars.
Now this is great because on the board we already have the principal elements of life.
Organic chemistry is the chemistry of carbon.
Carbon fuses next, and still heavier elements begin to form.
Sulfur, argon, chlorine,
potassium, calcium, scandium. The pace of this gets faster and faster.
Back in the middle, silicon is starting to burn at 3.5 billion degrees, stupendous temperature.
It makes titanium, vanadium, chromium,
manganese, cobalt, nickel, and iron.
Iron is really the end of the road. It's sort of the nuclear turnip out of which you just cannot squeeze anymore.
It's the end of the game. A star that has relied on fusion has come to the point where it has nothing more to spend.
The star is suddenly caught in a disaster. There's radiation going out from the outside, but deep in the inside, there's no more fuel.
Iron can't fuel the stellar furnace. And so, when a star builds up too much iron, it dies.
The core collapses, it bounces,
and it begins to move out, first slowly and then faster and faster.
And that sends a very sharp wave back out through the star.
And now what was falling down is going out, the whole thing's blowing up. And you make a supernova.
The supernova explosion can be as bright as 4 billion stars like the sun.
A stupendous explosion.
Such outrageous energies overcome the iron barrier. cooking atoms into all the rest of the elements on the periodic table.
So starting down here, you can go copper,
Zinc,
gallium,
germanium,
arsenic,
zirconium, niobium, molybdenum, technetium,
strontium,
rhodium,
potassium,
antimony,
terbium,
thorium,
thorium,
iodine,
radon,
xenon,
francium,
cerium, lanthanum,
tellurium,
cerium,
actinium,
actinium,
xenon,
thorium, protactinium, iridium. Done. That's enough elements.
So this is kind of the idea of, what the Big Bang was. And you can have your various different ways of believing in the Big Bang, but we know that through the process of stars is how we get all the elements up to what? Which was the last one they stopped at?
Iron.
So iron is the last one it can make, and then it goes supernova, right? The star dies. Then we get all elements till
Like uranium or something.
uranium. Yeah. So uranium is the last naturally made, the largest element made through the stars. So all these elements following, the ones that are in gray, these are our elements that are artificial. We made them as humans using these things known as particle accelerators, or their nickname is often called atom smashers. They're basically these
Smashes of atoms.
Yeah, it's what it sounds like. Is basically to make new atoms, we take other atoms and we smash them together, and then they hope that they'll stay together long enough that they can know that it's there before it breaks itself apart because they're so unstable, right? Okay, so with this idea of fission and fusion, okay, one of the take-home messages I want you to understand is the energy difference, the pros and cons of these two different sources of energy. Right now, when we talk about nuclear power, right, that our presenter talked about, his submarine, right, was fueled by a nuclear reactor, the nuclear reactors we have right now are driven through the process of fission, okay? The problems with fission is, one, our fuel is limited. There's not an unlimited amount of uranium on Earth. And if we run out of fuel,
we make more.
Then we
Particle
could
accelerator.
maybe make more, but that process isn't the easiest either, right? The other problems, right, that we've talked about are dangers of a meltdown. Toxic waste, that's a huge one, right? What did he say we do with it? We bury it, put it in mountains, right? But this is why a lot of people, and I told you this happened in Nevada, right, turn down nuclear power is because nobody likes the sound of this. Having waste that's radioactive for 10,000s of years in the mountain outside their house, right? And then there is a certain amount of thermal pollution that is produced as well. So then fusion, the cool things about fusion, right now it's a theoretical thing to be able to use fusion as a sustainable power, but it has some cool potentials because, one, there's plenty of hydrogen. The universe is 99% hydrogen, and then also the ocean has a lot of hydrogen too that we could extract if necessary. The other things, there's no danger of a meltdown, and there's no toxic waste. A fusion reaction doesn't emit radiation. The products are not radioactive compared to they are in fission. The biggest problem though is we have yet to sustain a reaction that requires 72 million degrees.